This table shows us some common international units. Okay? In the US, we use English system like a gallon, inch, yard, mile. Okay? But in science community, we often use international units because we want to talk to each other. If we use different systems, then we're going to get confused, as you can imagine. This table from your textbook shows us some common international units, and 5 of them are required. Okay, and here these are the symbols of those units. What do I mean by required? That means, for instance, if I write 5.5 lowercase m, that means 5.5 meter. Okay, 17.21 lowercase s, that means 17.21 second. Okay. Later on, when we do unit conversions and do other calculations, we need to see these units a lot. Okay, so I need you to memorize them. Temperature units. There are 3 temperature units: Kelvin, Kelvin, degree Celsius, degree Fahrenheit. Okay, this picture shows you the difference among the 3. Okay, but what are the mathematic connections among the 3? There are 2 equations. The first one is between degree Celsius and Fahrenheit. Okay, let me write it here. Degree Celsius equals to degree Fahrenheit minus 32 divided by 1.8. Okay, and the second equation is between Kelvin temperature, capital K, and the degree Celsius. K equals to degree Celsius plus 273. Sometimes you see folks using 2.3.15. Okay, either way, it doesn't matter which one you prefer. Okay, 273, 273.15. Either one of them is fine. What I expect here from you is, for the top equation, it will be given in your test or quiz if I need you to do any calculations involving the conversion between degree Celsius and Fahrenheit. But for the bottom equation, it's required. I need you to memorize it. Okay, when we do later on when we study thermodynamics and energy and a lot of calculation in Chem 2, we're going to do a lot of calculations involving the conversion between Kelvin and degree Celsius. So by remembering this equation, it will make your thinking process and calculation easier and faster. Okay. All right. Now, prefix multipliers. This is one of the most important parts of Chapter E. Okay. In order to get a good understanding of prefix multipliers, we need to know what scientific notation is. I believe you learned scientific notation in high school, so if you need to refresh your memory, please go to your textbook, Appendix 1, on page A1. Okay. In this review, you can see how you write a number by using scientific notation. Okay. And also in this math review part, you can also review the multiplication and division involving exponent part. Okay, so it's important for you to review this math part. Here in this video, we're going to just use the scientific notation directly. All right, now this table from your textbook shows us a bunch of different prefixes, symbols, and multipliers. Okay, 4 of them are required. 4 of them highlighted by red squares are required. I need you to be very familiar. I need you to memorize them. Okay, 4 of them. The others, if I need you to do any conversion, they will be given. Okay, they will be given. Now, how do we use prefix multipliers? The purpose of prefix multiplier is we can write a very large. We can for a large number, very large number, or very small number, we can use prefix multiplier to make it easier for us to write or use. Okay. What do I mean by that? Let's use this example to demonstrate. This question asks you to use prefix multiplier to express each measurement without exponents. Okay. Now, question A, 3.2 times 10 to the third meter. What this question is asking is, you need to find out the right prefix. and its symbol to replace 10 to the third. Okay, it has two parts, decimal parts and the exponent part. We need to use prefix symbol to replace 10 to the third. As you can see from this from this table, for 10 to the third, it has a symbol, prefix, to use. So this question is quite straightforward. The answer is going to be 3.2 kilometer. Okay, essentially we use k to replace 10 to the third. Okay. Now question B. Okay, 0.0021 second. This is a small number. Now the question for problem B is you don't see the exponent part. What we need to do is we use scientific notation to express this measurement first. Okay, let me show you. 0.0021, very small number. Okay, second. So how do we write the scientific notation? You move decimal point to your right 3 times. Okay, the goal is to move the decimal point to the right side of the first non-zero digit. Okay, here the first non-zero digit is 2, so you need to move the decimal point to the right side of 2. So that will come up with 2.1. When you move decimal point to your right, you need to multiply 10 to the negative n. N means how many times you move the decimal point. We moved the decimal point 3 times, so that means you need to multiply 10 to the negative 3 second. If you move decimal point to your left, you need to multiply 10 to the n. Okay. Anyway, now we have the decimal part and exponent part. So what we need to do next is to use the right prefix multiplier to replace 10 to the negative 3. As you notice again, 10 to the negative 3, the corresponding symbol of the prefix multiplier is milli. So what you need to do is just use 2.1, use milli m to replace 10 to the negative 3 millisecond. Okay, so this is a question B. Question C is a little bit different because if you take a look at the exponent part, 10 to the negative 5, but you don't see the corresponding prefix symbol for 10 to the negative 5. Okay, so what should we do? What we should do is we need to choose a prefix multiplier that is closer to 10 to the negative 5 and work on that. Okay, what do I mean? What do we need to do is, okay, question C, 22.73 times 10 to the negative 5 gram. Okay, I keep the 22.73 as the same, and then I split 10 to the negative 5 to 2 parts. The first part is 10 to the negative 6. The second part is 10 to the 1. Why do I split this 10 to the negative 5 to 2 parts? 2 reasons. The first reason is I've come up with the 10 to the negative 6, which has a corresponding prefix symbol to use. And then the second reason is by splitting to 2 parts, okay, the combination of these 2 parts will make sure that I don't change the value of 10 to the negative 5. What do I mean? Okay, let me show you. If you happen to remember the math, multiplication involving exponents, 10 to the a times 10 to the b, okay, that equals to 10 to the a plus b. And for our problem here, 10 to the negative 6 times 10 to the 1, that equals to 10 to the negative 6 plus 1. And that will give us 10 to the negative 5. So as you can see, I split the 10 to the negative 5 to 2 parts, but the value itself remains as the same. Okay. Now what we need to do is, okay, I'll combine these two items. Okay. And what we need to do is 22.73 times 10 to the 1 times 10 to the negative 6 gram. Okay. I open the parentheses and exchange the position of the two items, so the value does not change. Now I combine these two. That will give me 227.3 times 10 to the negative 6 gram. Okay. For 10 to the negative 6, the corresponding prefix multiplier is micro. So we need to just use micro to replace 10 to the negative 6. Microgram. Okay. So this is a question C. How about question D? Similar to question C, we need to come up with the right prefix multiplier for 10 to the negative 10. Very small number. Okay. You can see that from this table, 10 to the negative 9 is very close to 10 to the negative 10. So 10 to the negative 9 might be our target's prefix multiplier. Alright, now let me show you. Similar to C, 18.6 times 10 to the negative 10 mole. Okay. I split 10 to the negative 10 to two parts. 18.6 times 10 to the negative 9 times 10 to the negative 1 mole. Okay. Again, if you want to double check, let me write it here. 10 to the negative 9 times 10 to the negative 1, that equals to 10 to the negative 9 plus negative 1. That is still 10 to the negative 10. Okay. So the value remains the same. Alright, now I combine these two items. 18.6 times 10 to the negative 1 times 10 to the negative 9 mole. Okay, combine these two, that will give us 1.86 times 10 to the negative 9 mole. Alright, so the final answer, we use lowercase n right here, okay, to replace 10 to the negative 9. So that's going to give us 1.86 nanomole. Okay. Now, the units we talked about so far, they are basic units. Okay, they are basic units. But in science, there are some units called derived units, and the density is a very typical example. Okay. Before we talk about the density, let's talk about volume first. Volume is a measurement of space, and we use capital V to represent volume. Okay. And here this slide shows you some common units for volume: liter, ml, cubic centimeter, gallon, quarters. Okay. For gallon and quarters, in science we don't use them very often. Okay. And we use liters, ml, and cubic centimeter much more frequently. Okay, so and for those three units and their unit conversion equation, it's required. Okay, I need you to memorize this part. We'll use it for unit conversion later on. All right, now let's talk about density. How do we define density? Here is the equation. Density, capital D, equals to mass divided by volume. Okay. We use lowercase m to represent mass, capital V to represent volume. How about the density unit? Well, it depends on what unit you used for mass and volume. If you use gram for the unit of mass and the liter for the volume, then the unit of density would be gram per liter. If you use meg as the unit for density for mass and the cubic centimeter as the unit for volume, then the unit of density is meg per cubic centimeter. Okay. And one thing I do want to remind you here is density is an intensive property. Intensive property. Okay. It means the density does not change. Okay. No matter how much you have for the substance. For instance, if you have 10 grams of water, the density would be 1 gram per ml at 4 degrees Celsius. If you have 1 gallon of water, the density of this water at the 4 degrees Celsius is still 1 gram per ml. It doesn't matter how much water you have, the density remains the same. Okay, so this is what it means. Now, this table shows us the density of some common substances. Okay, like gold here, it's very heavy, as you notice. The density is 19.3. A quick example about how we calculate the density. Let's see, a platinum ring has a mass of 3.15 gram. Okay, and the volume of this platinum ring is 0.233 cubic centimeter. Okay, if you do the calculation of this of the density for this platinum ring, that will be something like this. So density equals to 3.15 gram over 0.233 cubic centimeter. Okay, and if you do the calculation, that will give you 13.5 gram per cubic centimeter. If you compare this density with the density of a platinum, 21.4 gram per cubic centimeter, it's much lower. That means this platinum ring is not real platinum. Okay, so we can use density intensive property. We can use this density to check whether this platinum ring is real or not. Okay. All right. Now, the energy and its units. Okay. Energy is a very common term we're going to deal with in chemistry. Okay. There are two types of energy. The first one is kinetic energy. Okay. That is associated with motion. Okay. And the other one is potential energy. Okay. It is associated with positions or compositions. Okay. So here, this picture shows you that energy can be converted from one form to another form. If you drop the iron from top of the building to the ground, then the potential energy of the iron is going to be converted to kinetic energy, motion. Okay. And for this picture, this guy is pushing this box forward. Okay, so the energy released by this guy is converted to the kinetic energy of this box. Okay, so later on when we discuss thermodynamics, you will see more examples about the energy conversion. Okay, and in chemistry, we care about the chemical energy. Okay, chemical energy is one type of potential energy. Okay, it's energy stored in chemical bonds. Okay, it's very common in our daily life. For instance, you eat your food, and when those food break into smaller parts, okay, the energy associated with the chemical bonds will be released, and that's how we synthesize the ATP and use that as an energy source. And here the methane gas, okay, the methane, the major component is CH4. When you burn it, you generate carbon dioxide and water, and when you break this bond, when you break the CH bond, the energy will be released. And the fireworks, the rocket, the energy fuel, the chemical fuel released by the rocket can push this spacecraft to move up. Okay, and the fuel, okay, the gasoline. I mean, this is typical chemical energy. Okay, all right. The next thing is about the energy and units. And here, this slide shows us some common units like a calorie, joule, and these are the unit conversion factors. they are not required. If I need you to do any unit conversion involving energy units, those conversion factors will be given. All right, so this is a unit of measurement. Let me know if you have any questions.